Hey, I'm Brendan Martin,
I'm Kyle.
and today we're going to be talking about unprocessing images for learned raw denoising. Suppose you get an image. It's going to be noisy. That's just a fact. How do you try to recover the true image that was supposed to be, the scene that was sending light into the sensor? How do you get something as close to that as possible, even though the information that you have is corrupted by noise? And so what we'll be talking about today is a paper which has presented a somewhat novel method of training a neural network to denoise images only from the single image without any reference to attempt to recover that raw picture.
For this project, we met quite a few times. We met April 7th for 10 minutes. That was the day that this project was given to us. We met April 10th for 2 minutes. We met April 12th for 3 minutes. We met April 13th for 2 minutes. We met April 19th for 20 minutes. We met April 21st for 2 minutes. We met April 22nd for 15 minutes. We talked on the phone April 24th.
I didn't want to see him in person. We were having a rough spat.
Yeah, we were fighting a little bit.
Yeah,
that was about a 5-minute phone call.
Yeah, right.
And then we met April 28th as well, which is, of course, today, as we're videoing this, we met for 1 hour.
And then there's the 1 minute we spent on this slide, of course. So typically, when you're training a model, the images that you get are going to come from online. They're going to come from sources that are, in general, unknown. You don't know what camera was used, and so you're going to have some mysterious noise that you don't want in your system when you train it, and you also don't even know how you got it. So it becomes important for getting good performance out of models to pre-process these training sets in some way to remove the noise, and so hence this paper has presented a better way to do so.
Yeah, so in this paper, the deliverable, which is this new method of training, claims a 14 to 38% lower error rate compared to the previous state-of-the-art method. And then it also is 9 to 18 times faster on this same, compared to that same method. And so these images on the right that we're looking at is the giving a noisy input image and then the ground truth reference image in A and B. And then C is the previous state-of-the-art method, and D is training with this new unprocessing method. If you look at these cropped images down below, we can see a difference between the previous model and our new model. There's some grid lines that we don't really prefer to have from the previous model, but in our model it has cleaned up and it does look a lot better.
You could just inject an additive white Gaussian noise to images in your training set and try to make it really noisy and train the model to denoise based upon those constraints. But if you just use pure additive white Gaussian noise, what assumptions are we making? We're assuming that this noise is spatially uncorrelated and that it's uniform across this entire image. But what we find is that our ability to model the real circumstance that we're encountering is critical to doing a good job. And so, is this assumption valid in real images? AWGN? Not all that so much. Another thing that's often done in other neural networks that have been trained for denoising before this one, they typically work in the RGB domain. And so we'll talk a little bit more about a different way to do this later on. But working in RGB may actually not be the right way to model the physical situation, because RGB pixels are not how the images are truthfully captured. So because that pulls us further away from the physical situation that the noise was captured in, any results that you generalize in a neural network from that is just going to be further away from the truth when you actually implement it.
The classical denoising approach is basically to just blur the image, and then taking this blurred, denoised image, we can sharpen it to further emphasize the high frequency details. But really, the best we could do when classically denoising an image is keep the same amount of information, and probably we're going to lose information in that denoising process. So it's not necessarily the best we can do.
Let's talk about the modification that they make in this paper as pre-processing to their training data images to make sure the noise is a more accurate emulation of true cameras. So there are two components of noise that are treated in this paper, and they're shot and read noise. Now, there are different assumptions for the different noises. Read noise is assumed to be uniform across every pixel, and read noise is a product of the process of reading the charge amount inside of each one of the cells in a charge-coupled device, a CCD, which is the basic sensor type used in cameras to measure how much light was coming in. And so because this is a product of the process of shifting that information out of the charge-coupled device into memory, it's roughly the same for all the pixels. They experience the same sort of transitions. And so that noise is truthfully pretty well uniform for all of them. Now, the other kind of noise that they've modeled in this paper is shot noise. And shot noise is a symptom of the discrete statistical nature of the arrival of these photons at the sensor. And it is related to the intensity there, because how many photons you're coming in is directly related to how much noise you're going to get from the arrival of photons, right? So they've got a model that takes both this non-spatially correlated and spatially correlated noises into account to model variance locally. So if you look at the model at the bottom of this slide, that y is being set to in here as normal as in a Gaussian distribution. Y is the image that they output, the noise image. X is the intensity values from the original image. And so you see read noise is being a component of the variance here that is totally uniform everywhere, and shot noise is getting scaled by the value at that location in the image signal X. And so this realistic model yields better results in the end. Another dose of realism that they add in this paper is not only working on images in the RGB domain, but they also work on images in the raw Bayer domain. And so, as you can see from this diagram, in a camera, each pixel is not red, green, and blue. It's only either red, green, or blue, and the same charge-coupled device is underneath them all, and these little color filters are selecting which color is being measured. But the noise process that you want to model, the noise that was actually captured, wasn't in the RGB domain. That doesn't exist anywhere in reality, at least to my knowledge. There's no pure RGB sensor that does them all at once. And so always the noise that you really are measuring is in the Bayer domain. And one of the cool ideas that they have in this paper is, suppose that we work in the Bayer domain, can we get better results? And we'll see the answer to that later. The other thing that's kind of nice about working in the raw domain, suppose that you could do it. If you could always just directly process raw images directly from a sensor, you're throwing away a processing step. And for the real-timeness of applications, that's pretty excellent. You don't have this conversion to sRGB, then the application of your neural network. You just pull in information directly from your sensor, denoise it, and then do whatever object recognition or whatever else you want on it. So especially for autonomous vehicle type applications, that would be particularly useful.
So the novel addition that this paper is trying to make, right, is this unprocessing technique, and then being able to train a network on that. And this is a pretty complicated process. There's a lot of things that a camera does when it takes an image to convert it from this raw Bayer format into the sRGB format that we upload to Instagram, right? And so to undo this, you first need to invert the tone mapping, and then you have to perform gamma decompression, and then you need to apply the sRGB to raw Bayer color correction matrix, and finally you have to invert any white balance gains or digital gains that have been applied to the system. And so once you do all those steps, right, you get this new raw image that you can use to train your model with.
But why would I do that, Kyle? Why unprocess an image?
That's a great question, Brendan. So when we train a neural network, you need to have a pretty large data set. And this data set can be very laborious to produce. It can be camera specific in a lot of cases. And you need to have really good noisy and ground truth data. And that's really hard to do. And there are approaches to create this synthetic training data, but lots of times they assume that the noise is additive, white and Gaussian, as we talked about earlier, and that just generalizes really poorly. And so with this image denoising pipeline that this paper talks about, we can convert to the raw Bayer image format, and the only noise that we need to apply then is the shot and read noise, which is really well studied and really well understood. And so you can very accurately model the synthetic data to replicate the real world applications.
Another wonderful advantage of this is that even though that the training image will have come from a particular sensor, by doing this, you can make that data seem like it came from a plethora of cameras, even though you only had one base image to work with, which is a lot more training data for the model to work on. Now, there is this question of why denoise with machine learning? What is it that's so fundamentally different about machine learning from the classical procedure that makes it worthwhile to look into? So the fundamental difference is that machine learning approaches can inject information into the image that isn't there because they already possess that image, that information in some sense within generalizations from the training data that they were given. They have these understandings, you could say, of primitive shapes. So maybe it knows that something looks kind of like a line, so it shouldn't vary off to the side, that it can interpret that must be noise because I know what a line looks like. That must be what that is. In the same way that when you see a chair, you might only spot the leg, but you know what the rest of the chair looks like. You see it every day when you go to class. And so you've got this information already stored within you about what is a chair, and that is allowing you to pick up extra information.
To train this data set, our paper pulls from the MIR Flickr extended data set. It's just a collection of 1 million RGB images. They're relatively high quality, they're pretty noise free, they're good images for training. They also, along with those images, they come with a lot of tags. They come with an EXIF file, and they also come with visual descriptors in case you need that for training your set. And so this gives a really large data set that they can programmatically unprocess and then create training and reference data for. And this beautiful image with a baby and a man doing yoga is image number 25,000 of the training set. So in this paper, they took the MIR Flickr training data set and they fed it into a neural network, and they used atom optimization to train this. Atom optimization just uses an estimate for the first and second order moments to train the network better. It's a pretty general neural network. And they trained 2 models based on this approach. They trained one that targeted minimum RGB error, and they trained one that targeted minimum raw image error. And training both of those sets took about 3 days.
Now, there is this question of how do you know that your network does a good job? Because we have to be able to evaluate the performance of this network compared to all the others. And so at the end of the day, it doesn't matter what we do in the digital domain. We need a real image, and we need these reference pairs. We need to have an image that was taken one noisy and one unnoisy, but that seems like a virtually impossible task. I mean, every single camera in the world that you have is going to have some noise. So how do you avoid this? Well, you can play a little bit of tricks with your camera and get something close. So you're never going to get a perfectly noiseless image, but what you can do is you can take a very good camera and you can take a long exposure image. And so for this case, you might have kind of a low ISO, which means that your aperture is small. And then the trick is they get a noisy image by cranking up the ISO. So they're letting a lot of light into the sensor at once. That means that they can't do it for as long. And so in that case, the noise is slightly more correlated. And so over that exposure period, the noise is much more stronger, it's more pronounced. And so in that way, this Darmstadt noise database was able to accumulate 50 images that are more or less noiseless and then quite noisy, but taken in the exact same place with the exact same camera.
So referencing this Darmstadt data set, we're able to validate our neural network and our processing method. And they have the Darmstadt dataset has the images in an RGB format, and they also have them in a raw format. And so in this paper, they take both of those and they feed both sets to each model that they trained. And as would be expected, the model trained to target RGB error performed better when fed with RGB images, and the model trained to target raw image error performed better when fed with raw images. And so they saw an improvement of 14.2% over for the PSNR over the state-of-the-art model, the previous state-of-the-art model. And they also saw an improvement of 24.5% in SSIM. They also saw runtimes 3 to 10 times faster than the next most accurate model. And it's also worth noting that the raw images actually performed 17% better than the RGB image model.
We believe that this paper contributes a significant advancement to improving the speed and processing on real-time data for neural networks and anything in the image domain, and is therefore quite cool to us. Hope you enjoyed it as much as we did. Thanks.